Okay, it's called the Wilcoxon signed rank test. Okay? And it differs from the last example. The last example we did was independent, and these are dependent. So again, a reminder, dependent events are like before and after scenarios or matched pairs, something like that. So they're dependent samples, okay? So I'll probably write that down, used for dependent samples. All right, let's jump right into an example and we can learn it as we go. 8 couples were given a questionnaire to measure marital compatibility, and after completing a workshop, they are given a second questionnaire. Has there been a change at alpha equals 0.10? Is there a difference in the before and after scores? Okay, so marital compatibility, a before and after scenario, and then and the question is, has there been a change at alpha equals 0.10 with their before and after scores? Great. So here we go. We have before scores and after scores. So let me just write these down on marital compatibility. Okay, so it's pretty obvious a before and after. So the first couple went from 43 to 48 on the scores. Then 52 to 59 for the second couple. 37 to 36. 29. No change for that one. 51 to 60. 62 to 68. 57 to 59. And 61 to 70. Okay, so we have 8 couples. So we'll leave a little bit of space to the right because there's a couple of columns that we need to do, and then we can go through and run the test, okay? So the first column that I would like you to do is just B minus A, before minus after. Okay, so everybody can do that. Just go through and do your before number minus your after number. And some of these are going to be negative, it looks like. Some are going to be positive. And just write those down. Okay, so for instance, I'll get you started. 43 minus 48 should be negative 5. Okay, and go on and complete that for me. Okay, so double check that I got these right. So I have negative 5, negative 7, 1, 0. Then negative 9, negative 6, negative 2, negative 9. Does everybody agree with that? Just doing B minus A, right? Okay, great. The next column, you're going to do the absolute value of the last column. So what does absolute value do, basically?
Changes everything to positive.
Yeah, any negatives pretty much become positives, and positives stay positives, and 0 stays 0. Okay? So this next column, we're going to call it the absolute value of B minus A, which is the absolute value of the last column. So now we have 5, 7, 1, 0, 9, 6, 2, 9. Okay. Then the next column, we're going to call that rank. R-A-N-K. Now, one thing that's a little tricky with the Wilcoxon signed rank test, if there is a 0, you completely ignore it. Okay, so if the before score was the same as the after score, that's the only way you're going to get a 0. You're going to ignore that one. Okay, so Pretend this one doesn't exist, just ignore. And if there was another 0, if there was another tie for before and after, just ignore that one too, okay? So zeros don't count for this rank column. And you guys are just gonna rank this, okay? So how do I rank again? Remind me. Starting with the smallest one, that gets a rank of what? 1, okay? And then a 2 will get a rank of 2. And then what's next? 5 here gets a rank of 3. 6 here gets a rank of 4. 7 gets a rank of 5. And then I'm on spot 6 and 7, and there's a tie for 6 and 7. So what's the rank for 6 and 7? 6.5. Okay? And again, if you weren't here, we did that last lecture. So please go back and review how to rank. You list the spots, and if there's a tie, the rank is the average of the spots. Okay, and then this test is called signed rank. So one more column, the signed rank. All right, and what you do is you're gonna look at this third column, and if the original sign was negative, you're gonna put a negative with the rank. If the original sign was positive, you're just gonna leave the rank positive. Does that make sense? So write down the ranks again, and if originally it was negative, put a negative next to it. So this is gonna be a -3, a -5, a +1, an ignore, a -6.5, a -4, a -2, and a -6.5. So it's the signed rank. The signed rank. Okay? All right. That'll get you as far as you need to be to do the test now. Okay? So let's do the test. The question was that alpha equals 0.10. Is there a difference? Okay, so step 1, HO and H1. Our assumption is that there is no difference between before and after scores. If there is, we're going to put that into H1. So our assumption is no difference. There is. Okay, and that's the end of HO of H1. Okay, step 2, we're going to go to the table in our book to get the critical value. And this is table K, critical values for the Wilcoxon signed rank test. Okay? A couple of things. Alpha is 0.10. It's two-tailed because it's no difference versus there is a difference. And then N, we have to be careful. N is all the ones that don't have 0 as a difference, okay? So there were 8 couples, but one couple had the same before and after score, so that couple doesn't count, okay? So N is the number of matched pairs. That was an easy way to say this. Where the difference is not 0. Does that make sense? Where difference is not 0. Okay? So we had 8 couples, and we're looking at their marital compatibility. One of them had a before and after score that was the same, so they zero out and they don't count. So instead of N equals 8, our N is going to be 7. Okay? And if 3 or 4 couples match, then you just drop them out as well. And again, we didn't rank those. Okay? So another way of doing it is counting how many sign ranks you have, because you don't rank the ones that were 0. All right, so let's look that up in the book. So N is 0.1, it's two-tailed, and N here is 7. So what do we get for our critical value, everybody? 4. Great. CV is 4. Okay, and then we move right along into the test value. Here's your test value formula. You sum up all of the positive ranks, and you sum up all of the negative ranks, okay? So sum of the positive ranks. If I sum up the positive ranks, that was really easy, it's just 1. And then I sum up the negative ranks. So -3, -5, -6.5, -4, -2, -6.5. You add that up. What is that? -13, -27, is that right? Guys, double check my math on that.
Yep.
-27? Okay. Okay, so here's your test value. You take the absolute value of both of these, and whichever is smaller, okay? Because if you look at a negative number and a positive number, the negative number is always going to be smaller. That's why you have to take the absolute value of it, okay? So your test value formula is you take the absolute value of this, the absolute value of that, and whichever one's smaller, okay? So if I take the absolute value of 1, you get 1. If you take the absolute value of -27, you get +27. Which one is smaller? 1, okay? So my test value is 1. So whichever is smaller after you absolute value. Okay, so steps 1, 2, and 3 are complete. Step 4, if your test value is less than or equal to your critical value, you reject HO. Is my test value smaller than or equal to my critical value in this problem? Yes, 1 is smaller than 4. So reject HO. If I reject HO, I'm saying, we're not saying there's no difference, which means there is a difference. So your conclusion for this is yes, there is a difference in the before and after scores on marital compatibility. Okay? That is the Wilcoxon signed rank test. It's fairly easy, it's fairly straightforward. Just be really good on ranking it and then just putting your original sign back. And that's what we sum up. You sum up your negative signs, you sum up your positive sign ranks, and that's how you get your test value. Question?
Could you go over the test value and stuff too?
Yes, no problem. So on this column here, you add up all the negative numbers together. And that's the summation of the negative ranks. Okay? So when I add -3, -5, -6.5, -4, -2, and -6.5, it came out to -27. And then you also want to add up all of the positive ranks. Well, we got lucky in this one. There was only one positive rank. There was only one positive, so it's 1. So the sum of 1 is 1. Okay? That's the first step in the test value. Then you have to take the absolute value of both numbers. So the absolute value of 1 is 1. The absolute value of -27 is +27. And then whichever one's smaller, that's your test value. Yes. Okay, any other questions? Okay, that is Wilcoxon signed rank test. Great. Let's move to the next one, which is the Kruskal-Wallis Test, also called the H test. And that'll be the last test we do today. Okay, Kruskal-Wallis, K-R. Kruskal-Wallis, also called the H test. So if in your book it says H test, that's the test we're talking about. Okay? This is our non-parametric version of ANOVA. All right? Does anybody remember what the ANOVA test tested? If there was a difference in 3 or more means, right? So 3 or more means. So this is our non-parametric version of testing 3 or more means, okay? Okay, so I'm going to show you how to do the test, but I need to tell you what the critical value uses the chi-square table, okay? So the critical value comes from the chi-square. And on the chi-squared, the degrees of freedom is going to be k minus 1. And again, so that's how many samples or how many groups you have, minus 1. And it's always going to be a right-tailed test. Excuse me. And that's good because our chi-square distribution is set up for a right tail. So that plays to our favor. All right. Let's put up a problem on the board and then we can walk through it together. A test to measure self-esteem is given to 3 different samples of individuals based on their birth order. At alpha equals 0.05, is there a difference in the scores? Okay, so we're looking at birth order, the oldest child, middle child, and youngest child, and they gave them scores based on self-esteem. And then the question is there a difference in the scores? Okay, so let's write down the samples. So we have oldest child, I'll call that OC for oldest child, MC is middle child, and YC is the youngest child. All right, so the oldest child, the scores were 48, 46, 42. And 41, 37, 32. 41, 37, 32. Okay, that's the oldest child's scores. Middle child's were 50, 49, 42. 50, 49, 42. And 43, 39, 28. And the youngest child was 47, 45, 46. And 30, 32, 41. Okay, so before we do this test, let's go ahead and get the ranking out of the way. So what we want to do here is pretend all of this is one huge sample, and we're going to rank all of the values, okay? And then just put your ranks next to the numbers. So I'll just put them in parentheses to the right. Does that make sense? So I've already done it in the notes, but if I were to start ranking this, which is the smallest number here? 28, right? So that would get a rank of 1. Everybody with me? What's the second smallest number?
30.
30, so 30 would get a rank of 2. Great. What's next? How many 32s are there? 2. So this is spot 3 and spot 4. So that would get a rank of 3.5, 3.5. And then you would continue on with spot 5. Excuse me. Okay? So just keep going and keep going. I'm going to go ahead and put these on the board for you. But don't look up yet. Just do the ranks yourself and see if they match up with what I got. Take your time, just go through each one, rank it. It's a little tricky because there's a couple of ties in there. Any questions or problems on the ranking? Did everybody get this? Okay, so just be careful. We're pretending it's all one huge sample, and we're just ranking it just like we've done the last couple of days. All right? I'm going to move on, so let's actually start the test. We haven't even started the test yet. So HOH1, again, this is a good one because it's always the same. Your H is going to be there's no difference, right, in the scores. Your H1 is going to be there is a difference. Okay, that's the end of step 1. Step 2, go ahead and find the critical value for me. I told you it was chi-squared. I told you it's always right-tailed. And I also told you the degrees of freedom is k minus 1. K is how many groups we had? We had 3 groups. Oldest children, youngest children, and middle children. Did I tell you what alpha to use?
No.
0.05. So draw your chi-square distribution. All of it's in the right tail. 0.05. K minus 1, so my degrees of freedom is just 2. And look that up for me. Should be pretty easy because chi-squared is set up right tail data. What do you get? 0.05, 2 degrees of freedom, 5.991. Okay? You literally just looked it up. I don't have to make any adjustments because our table is set up for right-tailed area. Okay? All right, now I need to tell you what the test value formula looks like. It's H equals, that's why it's called the H test sometimes. H equals, here's your formula, 12 divided by capital N times capital N plus 1. Please make sure that's a capital N, that's not a lowercase n. Times, big parentheses, R1 squared over small n1 plus R2 squared over small n2 plus dot 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 however many r's you have. So I'm going to put RK squared over small nk. Okay? Then minus, and don't miss this out, 3 times capital N plus 1, close parentheses. That's your formula. 12 divided by capital N times capital N plus 1 times R1 squared over N1 plus R2 squared over N2 plus however many groups you have. In this case, we're only going to have 3, but you could have 4 or more. Minus 3 times capital N plus 1. And I would almost circle this piece here because for some reason, in the last few years I've been teaching here, students always forget that last piece. So star it or something, don't forget that last piece because you get so overwhelmed with the ranking part, you just forget about that. Okay? All right, so I need to tell you some things. Capital N is the total number, all of the samples, right? So in this case, I think I had 6 in each sample, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Great. So capital N is 18 for this problem. It's the total number that we have, or the sum of all the sample sizes. Okay. N1 is how many was in sample 1. N2 is how many is in sample 2, so on and so forth. R1 is the sum of the ranks in sample 1. R2 is the sum of the ranks in sample 2. Okay? So come back up to R1, R2, and R3, and here we go. R1 is going to be the sum of these ranks. R2 is going to be the sum of these ranks. And R3 is the sum of these ranks. So you had to rank them, and then just sum each one per group or sample that it's in, and that's going to be capital R1, capital R2, capital R3. Okay? So if I add 16, 13.5, 9.5, 7.5, 5, and 3.5, what is that? That is 55. So your R1 is going to be 55. Okay? Your R2 is going to be the sum of these ranks, 18, 17, 9.5, 11, 6, and 1. And in my notes, I came up with 62.5. So R2 is 62.5. And finally, R3, 15, 12, 13.5, 2, 3.5, and 7.5. And I got 53.5. Okay? It's crucial that you get these ranks right because, look, you're going to square these numbers. All right? So you're really going to make these numbers a lot bigger, so make sure that your ranks are correct, because when we square them, obviously, you're going to increase error if you've messed up. Okay? All right, we're pretty much done, so let's do this. You have 12 divided by 18 times 19 times R1 squared, 55 squared, divided by 6. And again, on this particular example, all of the samples were 6. But structurally, what this means is divided by however many you had in group 1, divided by however many was in group 2, divided by however many was in group 3. It's not always the same in 6. You know, there could have been 7 in the second group, there could have been 10 in the third group. So just be careful with that.
What's the K? RK?
That's the number of groups. Okay? So the second one is 62.5 squared, and there were 6 in that group, plus the third one is 53.5 squared, and there were 6 in that group. And then what did I say a minute ago? Don't forget the last portion, and everybody drops this. Don't forget your minus 3 times 19.
I'm sorry. After your R squared 2 plus, is this RK squared divided by NK?
Yes.
That's your dot, dot, dot. That's just an example for how many more groups?
Yeah, because this one only had 3, so it's going to be R1, R2, and K is 3.
Mm-hmm.
But it could have had 8.
Okay.
Right, so you'd have R1, R2, R3, R4, R5, all the way up to 8. So I just put K there because it goes up to however many you have, how many groups you have. Okay? All right, be super careful when you plug this into your calculator. 12 divided by parentheses 18 times 19, enter, times all of that. You can put all of that parentheses in 1, and then minus 3 times 19. So I will do that with you, and let's see what we get here. Okay, all of that, and I only got 0.2719. So all of this for me came out to just 0.2719. Pretty small number. 0.2719. Obviously, that's not going to be in the rejection region. It's over here somewhere. So my test value is not in the rejection region. So step 4, do not reject HO. By not rejecting HO, we're saying there's no difference. Bless you. So the question was, is there a difference in self-esteem based on birth order? We didn't find that there was. Okay? Doesn't appear to be a difference in self-esteem scores based on birth order. So as long as you know what you're saying, that's what step 5 is. Your conclusions in your own words. No difference in self-esteem scores based on birth order. Okay, be careful plugging this one in your calculator. It might be a good idea to separate this, then that. Any questions? Okay.